online data challenge poses a scenario that calls for a machine learning program to identify a spooky author based on a sample of his or her text from samples of various works. But how exactly is this problem related to machine learning? Many challenging and interesting problems in machine learning are inspired by processes that we do every day, like visual processing and language processing. One such problem is how to identify an author based only on examples of his or her words. A common solution we found in our literature review were Markov chains and hidden Markov models. Markov models are classical machine learning techniques that are especially useful for processing temporally dependent information like weather, financial markets, and, most relevant to our project, language. Markov models use a present state to inform what a future state will be. These models make two major assumptions. Given the present, the future relies only on the present and not on the past, and that the relationship between different present states and corresponding future events does not change over time. Markov models can be extended to consider more events as informing future events as well by increasing the number of layers, as demonstrated by the lower portion of the figure on screen right now. The bottom shows a second-order Markov chain. But what happens in a more realistic scenario when these states are not necessarily directly observable? In this scenario, we can use hidden Markov models, or HMMs, which allow us to use observations to inform about these hidden states. HMMs have been implemented in a variety of applications relevant to language processing, such as speech recognition, handwriting recognition, and speech synthesis, and even author verification, which is why it's relevant to our problem. This, along with the sequential nature of our data, led us to the conclusion that an HMM would be an appropriate model for our spooky author identification program.
We implemented our hidden Markov model using Python 3.5. In our literature review, we found two main approaches for HMMs, a word-based model and a character-based model. We developed both to compare. We evaluated both with 1, 2, 3, and 4 hidden layers. This effectively means our model looked at 2 to 5 words at a time for its classification. Our early model was 1-layer word-based. We initially got a 99% accuracy, which was a red flag for overfitting. This is a common problem of HMMs when dealing with a limited dataset. Per perspective, our dataset includes just under 20,000 samples, while current successful implementations of HMMs for comparable problems train on datasets with closer to 1 million examples. Thankfully, overfitting can be addressed by using cross-validation. We implemented a 10-fold cross-validation and the accuracy dropped to 74%. We then implemented a 1-layer character-based model and got an accuracy of 40%. We next tried to improve this accuracy by increasing the number of hidden layers. We found that the accuracy of the word-based model went down with additional layers, while the accuracy of the character-based model stayed the same. We believe this is again due to our limited data set and the limited size of each example.
With increasing numbers of hidden states, there was also increasing rise time, which makes sense as there was also increasing computational cost. Ultimately, our best model was our first-order word-based model with an accuracy of 74% and a median runtime of 15 seconds. One of the major limitations of this project was the dataset, both in terms of number of samples and the size of samples. In spite of this, we were still able to achieve fairly reasonable results with our hidden Markov model. If we had started with a much larger dataset, a more optimal solution could have been a recurrent neural network, which would have allowed for a solution that would be generalizable across many other examples of author identification, rather than just for spooky authors. But the poor performance of our higher order HMMs in terms of both accuracy and runtimes is a good indication that this dataset just did not have enough examples for the computational cost of training an RNN. For more information and for a Python 3 code implementing our first-order word-based HMM, please see the website linked in the description box.